In previous videos, we've learned how to draw Lewis structures, and when we did that, it was suggested that drawing Lewis structures could help us determine the shapes of molecules. But it was also suggested that the Lewis structure is not necessarily the shape of the molecule. So in this lecture, we're going to learn about how we can use the repulsion that electron pairs have for each other to predict the shapes of molecules and other covalently bonded species. The idea behind this is something called VSEPR theory, and the V, S, E, and P, and R each stand for a word that lays out the thinking behind this theory. The first two letters, V and S, are for valence shell. So we're talking about the outside shell of the atom. The next two letters, E and P, stand for electron pairs. So if you put these four together, we're talking about electron pairs that are in the valence shell. And then the last letter is R, which is for repulsion. So it's the repulsion of outer shell electrons for each other that helps us to predict what the shapes of molecules should be. The reason this works is because electron pairs, all being negatively charged, are repulsive to each other. So they're going to spread out in space as much as they possibly can, and that's going to dictate the shape. Let's get into how this works. We're going to use a tool from PhET that allows us to build molecules, electron pair by electron pair, bond by bond, and get a kind of a three-dimensional look at what the shapes are going to be. If you have only two atoms, they're just going to be attached to each other and just going to be a straight line between them. So that's a trivial case. The first instance where it's going to be in any way challenging to figure out what the shape is would be when we have three atoms bonded together. So a central atom and two outside atoms. So I'm going to introduce this idea called steric number. The steric number is the number of regions of electron density around the central atom. So a bond counts as a steric number, a double, single, or triple each count as one steric number, and an electron pair counts as one as well. So if you add up the number of bonds and the number of lone pairs around a central atom, that is that atom's steric number. So the simplest case would be a steric number of 2, where you only have two regions of electron density, and let's say that none of them are lone pairs, so it's two bonds. If you want to, there's a little bit of a code that you can use, and this might be helpful if you're not very good at thinking spatially, but are good at remembering things. Memorizing this code, AB2, might help you to pair together a shape to a Lewis structure type. So the A stands for the central atom in the middle, and the B stands for the atoms on the outside. In this simulation, the purple sphere represents the central atom, and then we have outside spheres that represent bonded atoms that are on the outside. Let's add a bond, and then let's add a second bond. So we have a steric number 2 on this purple atom. There's two regions of electron density, and they are the electron pairs that make up the bonds. Those are the sticks in this structure. VSEPR is built into this simulation. So as soon as the bonds are added, their repulsion for each other is programmed into the sim so that they're going to automatically spread out as far apart as they can be in three-dimensional space, which turns out to just be a straight line. So no matter how I spin this around, you can see that these things are 180 degrees away from each other. So the geometry of the electrons is what we call linear, and the molecule itself is also a linear molecule. It's a reasonable name because it's a straight line. The angle between these two regions of electron density, between these two bonds, is 180 degrees, and that's pretty easy to see just by looking at the shape. So when the steric number is 2, and both of the electron pairs are bonds, in other words, there are no lone pairs, we have a linear electron geometry and a linear molecular shape. This is easy to sketch. The sketch just looks exactly like what we have here in the simulation. Central atom, I'm going to make that in dark, and the outside atoms are hollow. And my sketch isn't very good because it's hard to draw on this thing, but those should be 180 degrees from each other. That's the bond angle. The next case that's of any interest is when the steric number is 3. If one of those bonds was replaced by a lone pair, In other words, lone pairs equals 1, steric number equals 2. Then it's just two atoms bonded to each other, and that's just a straight line. It's not of much interest. Coming back to our simulation, we have our linear molecule. Let's add another bond, and the bonds automatically arrange themselves in space as far apart as they can be, and we can see that they are in a flat plane. And so this is called a planar shape, and it makes up a triangle. If you think about sketching the shape of the outside atoms, it's a triangular shape. The electron geometry is called trigonal planar or triangular planar, and the molecule geometry is the same. We'll find that when there are no lone pairs, the molecule geometry and the geometry of the electron pairs will have the same name. Let's look at the bond angles. It's not too hard to figure out that if you are spreading 3 regions of electron density out in a 360-degree circle, the bond angles would be 120 degrees. So if the steric number is 3 and there are no lone pairs, that would be what we call an AB3 molecule. So A is for the central atom. The 3 Bs are the 3 outside atoms. We have seen that this makes a electron geometry that's flat and triangular, trigonal planar, and the molecular shape is also trigonal planar. And we've seen that the bond angles are 120 degrees. Sketching this is pretty easy because it's a flat molecule. So you put your central atom there, and then as best you can, you're going to draw 120 degree bonds out to your outside atoms. The next case that would be of interest is if we have a steric number of 3, but one of the regions of electron density is a lone pair. So let's consider that next. We're back to our trigonal planar molecule. What we're going to do is we're going to take one of the bonds away and we're going to replace it with a lone pair. What we can see happening is that the bond angle still stays around 120, and actually the lone pair is more repulsive than a regular bond because it can spread out a little bit more. And so that means that that bond angle is actually going to be a little bit smaller than 120 degrees. The electron geometry is still trigonal planar, but now the molecule isn't a flat plane anymore. The molecular geometry is what we call a bent or a bent 120 molecule. So if the steric number is 3 and there's one lone pair, that would be what we would code as an AB2E molecule, A for central atom, B2 for 2 outside atoms, and E for a lone electron pair. The electron geometry is trigonal planar, just like it was before that lone pair was replacing the bond, but the molecular shape is a bent 120 because of the 120 degree bond angle that it retains. So the bond angle is 120. It's very simple to sketch this because it's planar. So you just draw your central atom and then try to draw as best you can 120 degree angles to the outside atoms. So here we have trigonal planar. We have 3 outside atoms bonded to one central atom. Let's add another bond to another atom. Okay, now we can see as we kind of pivot this thing around that we no longer have a flat shape. In 3-dimensional space, the farthest away that these can get from each other does not result in a flat molecule with 90-degree bond angles. Instead, we get this geometry here. The electron geometry is tetrahedral, and of course, since there are no lone pairs, that means the molecule is also tetrahedral. And the reason it's called tetrahedral is because this makes a 4-sided figure. It's like a pyramid with a triangular base, 4 sides to it, and the bond angles turn out to be 109.5 degrees away from each other. So if you do the solid geometry, that's the ideal bond angle to minimize the repulsive forces between all of these electron pairs. And it's symmetrical, which will turn out to be important later on. So if steric number is 4 regions of electron density around the central atom, and the number of lone pairs is 0, that's what we would code as an AB4 molecule. We saw in the simulation that the electron geometry is tetrahedral. Here you can see that 4 sides of the tetrahedron sketched out in the red dotted lines. And the molecular shape is also tetrahedral. And we've seen that the bond angle is 109.5 degrees. These are a little bit trickier to draw because they're not flat. Here's a kind of a standardized way to draw this, even if you aren't a good artist. Draw your central atom and then go up with one of your bonds, then try and simulate a 109.5 degree angle. This would be a flat plane. Now, the third one we're going to draw as a little bit of a triangle that's solid and it gets bigger as it goes down. That's meant to simulate that it's coming out of the page or out of the screen. And then the fourth one we're going to draw also as a triangle, but it's going to get smaller and it's going to be hollow. And that's meant to simulate that that's going kind of back into the screen. And that's sort of the standardized way to draw a tetrahedral structure. Okay, the next thing that will be interesting to consider is what if we have steric number 4, but we have a lone pair. Here we are with our tetrahedral molecule again. And what we're going to do is we're going to take away a bond and we're going to replace it with a lone pair. You can see now that it still retains the electron geometry of a tetrahedral. That electron pair continues to be repulsive, and that makes this not a flat, like a triangular planar molecule. The molecular geometry is called the trigonal pyramidal. It's because it's a pyramid that has a triangular or trigonal base to it. The bond angles are still going to be around 109.5, but they're probably going to get pushed a little bit closer because of the extra repulsion on that lone pair. So if we take away the view of the lone pair, the molecule that we have left, you can see that it's a pyramid with a triangular base. So if our steric number is 4 and one of the regions of electron density is a lone pair, that's what we would call an AB3E molecule. The electron geometry is still tetrahedral, but now with looking only at the molecule itself, the molecular shape is trigonal pyramidal because it looks like a pyramid with a triangular base. The bond angles remain about 109.5 degrees, and sketching it, it's going to be very similar to when you sketch a tetrahedral. You just don't have that bond that's up at the top. You're going to draw this solid triangle as a bond meant to look like the bond's coming out of the page, and then that hollow one that's meant to look like it's going back into the page to try to give a three-dimensional effect. There's one more steric number 4 that's of interest, and that's when we have 2 lone pairs. So here's our trigonal pyramidal molecule, and we are going to take away another bond and replace it with another lone pair. And we can see that the lone pairs, again, continue to have influence over the shape. So even though there's only 2 outside atoms, it's not linear, it's instead bent. And the molecule geometry is also called bent, like it was before. The bond angle is around 109.5 degrees, but it's actually much smaller than that. It's small enough that we call this a bent 105. So those angles get compressed down to about 105 degrees. So if the steric number is 4 and there are 2 lone pairs, we would code that as an AB2E2, 2 outside atoms, 2 lone pairs on the central A. Electron pair geometry is still tetrahedral, but we can see now that the molecular shape is just down to a bent, and it's a 105-degree bond angle, so we call it a bent 105. Also easy to sketch because we're back to being a planar molecule, so you just draw that bent molecule in one plane. The next shape that we'll have any interest in exploring is when steric number goes up to 5. If you have steric number 4 with 3 lone pairs, again, we're back to just a stick, just 2 atoms bonded to each other. Okay, here we're back to our tetrahedral molecule, and we're going to add an additional bond. When we do that, we find that we have 2 different bond angles present. If we show the bond angles, one set of bond angles is 90 degrees above and below what looks like a flat plane. But if we take another view of it, we can see that that flat plane, let's just look at it right from the end, we have a 120-degree bond angle. So this is like a trigonal planar or a triangular planar, but with a linear molecule kind of stuck through it. The electron geometry here is called a trigonal bipyramidal. It's like 2 pyramids that have a triangular base they share the same triangular base. And the molecular geometry is also trigonal bipyramidal because we have no lone pairs here. So if the steric number is 5 and there are no lone pairs, we would code that as an AB5. We have seen that the electron geometry is trigonal bipyramidal. And here we can see the triangular base that the 2 pyramids share. There's one pyramid going down towards the bottom and the second pyramid going up towards the top. The molecular shape, also a trigonal bipyramidal. There are 2 different bond angles, as we've seen also. The bonds in the equator are 120-degree angles. Those are the ones that are shown sketched out in green. This is like, think about the equator and the axes of the Earth. The axial bonds are 90 degrees away from that equator plane. Once again, it's not very easy to sketch, but there's a standard way to do it. The first thing that I drew is I just draw a triangle that's meant to look like an equilateral triangle that's kind of been tipped over. And then I'll draw the central atom in the middle of there, and each of the corners I'll put my equatorial atoms. So the equatorial bonds go like that. And then one straight up, one axial, and then another one straight down underneath. So that's a standard way to draw that arrangement. Now let's stay with the same steric number, but let's replace one of the bonds with a lone pair. Before we do this, let's make a little prediction. The equatorial bonds are 120 degrees away from each other, and the axial bonds are only 90 degrees away from other bonds. So there's more space for that more repulsive electron pair to fit in the equator than it is as an axial. So when I remove this and replace it with a lone pair, we'll see that it keeps itself in the equator. The molecular geometry is sometimes called a asymmetrical tetrahedron, but the one that I like better is called a seesaw because it's pretty descriptive. If I think about moving this up and down, it's like a kid's playground equipment of seesaw. So if we have a steric number of 5 and we have one lone pair, we would code that as an AB4E. The electron pair geometry continues to be trigonal bipyramidal, but the molecular shape is a seesaw shape. Once again, we have two different bond angles. The bond angles are 120 degrees in the kind of the fulcrum of the seesaw, because that's the equatorial plane, and then it's 90 degrees between the fulcrum and the two sides of the seesaw. Sketching this, we're going to again make use of that trick where we draw what looks like a flattened over isosceles triangle. We're going to put our central atom in the middle, and then we'll put equatorial there, so those are like the fulcrum. That's a lone pair, so we're not drawing it. And then one axial up, another axial down. Next thing to consider would be if we had two lone pairs with a steric number of 5. Here's our seesaw molecule. We're going to remove a bond and replace it with a lone pair. And we still see that the lone pair belongs in the equator because there's more room for it to spread out and it's being more repulsive. And the shape, even though there's 3 outsides and 1 inside, is not triangular planar, but because of those lone pairs, it's actually shaped like a T. So if we have a steric number 5 and 2 lone pairs, the code's going to be AB3E2. The electron geometry is trigonal bipyramidal, but the molecular shape is T-shaped, and now we only have one bond angle and it's 90 degrees. And also, we're back to an easy to sketch molecule. T-shaped is flat, so we just draw a T, central atom at the kind of the crux of the T, and at each of the points we would have an outside atom. Okay, we still have one more electron pair that we can remove before we're down to just a straight stick again of only 2 atoms. Here's our T-shaped molecule. We're going to take away a bond and replace it with a lone pair. And as you might have predicted, it's going to go in the equator just because those repulsive electron lone pairs need more space to spread out. And this results in a molecule that's just linear, just a straight line molecule. So a steric number 5 with 3 lone pairs would be coded as an AB2E3. The electron pair geometry is trigonal bipyramidal, but the molecular shape is linear. The bond angles are 180 degrees, and sketching it, of course, is very simple. It's just a straight line like that. Okay, we're done with steric number 5. Let's step it up one more step and make steric number 6, because we know that we can have expanded octets for some atoms, and so it's possible to have 5 or 6 atoms bonded to a central atom. Here's our trigonal bipyramidal molecule. We're going to add another bond, but before we do, think about where is this likely to go. If we bisect a 90-degree angle, there's not as much room for that extra electron pair as if we bisect a 120-degree angle, so this is probably going to go in the equator. In fact, that is what happens, and we end up with a symmetrical molecule. The electron geometry here is called octahedral, and that's because if you connect all the outside atoms, you end up with an 8-sided figure. Another name for it could be a square bipyramidal, because we have two pyramids that share a square base. Molecular geometry, of course, is octahedral as well, because there are no lone pairs. And if we look at the bond angles, it's 90 degrees everywhere. So if we have steric number 6 and there are no lone pairs, we would code that as an AB6. We've seen that the electron geometry is octahedral. There's the square base, and then there's a lower and an upper pyramid that end up making an 8-sided figure. The molecular geometry is the same, octahedral, and we have seen that all the bonds are 90 degrees. Drawing this, we're going to, instead of using a knocked over isosceles triangle like we did for trigonal bipyramidal, we're going to use a knocked over square, which kind of looks like this rhombus. Central atom in the middle, outside atom here, 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 and here. There's our bonds. Those are 90-degree angles, even though on perspective it doesn't look like that. And then one up here, kind of like an axial in a trigonal bipyramidal. And one down here. Sorry, that should be hollow. Okay, let's do two more. One of them is going to be steric number 6 with a lone pair. Here's our octahedral molecule. We're going to take away a bond and add a lone pair. And because of the symmetry, it really doesn't matter which one we take away. When we add a lone pair, it's just going to have to go in that spot. If we look at this molecule with this kind of perspective, we can see that this is a pyramid that has a square base. And in fact, that's the name of the molecular geometry, square pyramidal. And the bond angles continue to be all 90 degrees everywhere. If we have a steric number 6 with one lone pair, that would be coded as AB5E. The electron pair geometry is still octahedral. But the geometry of the actual molecule is a square pyramidal shape. You can see the square base, and that upper atom connects to all the base atoms and makes a pyramid. Sketching this, we can still make that knocked over square. Outside atoms here, 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 and here. Central atom in the middle. Now we go up to that top atom, but there is no down atom. Okay, one last shape. Let's consider two lone pairs with a steric number of 6. Here's our square pyramidal molecule. We're going to remove a bond and replace it with a lone pair. Remember, lone pairs are extra repulsive, so the smart place for this thing to go is exactly opposite, 180 degrees away from the existing lone pair, because those are the two that are the most repulsive. So when we take it away, replace it with a lone pair, we can see that's exactly what happens, and we end up with a flat molecule that's called a square planar. The bond angles continue to be 90 degrees. So if the steric number is 6 and there are two lone pairs, that's an AB4E2. The electron pair geometry continues to be octahedral, but the molecular shape is a square planar. And once again, we're back to something flat, so this is easy to draw. Put that central atom there, and you can just literally draw right angles to all the outside atoms because the bond angles are all 90 degrees. Those are all the shapes that we're going to consider here. And next, let's look at how we can predict what the molecular shape is from a formula. If we want to predict the molecular shape from a formula, the first thing that we want to do is draw the Lewis structure. Just follow the normal rules for drawing Lewis structure. As always, if you have some concern about could you make a better structure, check formal charges and try and make other structures if needed. Find the steric number by just counting the regions of electron density around the central atom. And if there's multiple central atoms, which you have with some more complicated molecules, then you may have to do that more than one place. From the steric number, get the electron geometry. So if it's steric number 2, that's going to be linear. Steric number 3, trigonal planar. Steric number 4, tetrahedral. Steric number 5, trigonal bipyramidal. Steric number 6 will be octahedral. Then looking at the contrast between the number of lone pairs and the number of bonds that you have, you can get your molecular shape. So just for one example, if you have steric number 5, that's going to be electron geometry that's trigonal bipyramidal. And if you have one lone pair, that's going to end up being a seesaw. So you kind of have to either memorize those patterns or visualize it in your head. And a little bit of practice makes it go a little bit better too. Let's do an example, carbon dioxide. First, let's draw the Lewis structure for carbon dioxide. We've done this one before. There's going to be 4 plus 12, that's 16 electrons in the structure. Put the carbon in the center, oxygen on the outside. We fill the octets. And count, and we find we have too many electrons. That's 20. So we end up taking an electron pair away, there and there, making a double bond, and then doing the same thing. The other oxygen, make it another double bond, and there's our structure. Okay, so now we have a Lewis structure. Second, find the steric number. There are only 2 regions of electron density around that central carbon. It's the 2 double bonds. So that means this is going to be linear. We have no lone pairs, so that means the molecular shape is also going to be linear. Here's another one, BCl3. Boron's going to give us 3 electrons. 3 chlorines are going to give us 21 electrons. Put boron in the center, put the 3 chlorines on the outside, fill octets. When the chlorines, boron does not get a full octet. It's an exception. It only has 6 electrons needed for stability, and it has those in the 3 bonds. So if we count, we have 6 electrons around each chlorine in lone pairs. That's 18 for lone pairs. Then with the bonds, 20, 22, 24 electrons, and 3 plus 21 was 24 electrons. So that's a good electron count. Okay, we have a Lewis structure that's valid. Steric number is going to be 3 because there are 3 bonds around boron and no lone pairs. So it's trigonal planar electron geometry and also trigonal planar molecular shape. NO2 1 minus. Nitrogen 5 electrons. Oxygen 6 each times 2 is 12. So 12 electrons plus another electron because of the -1 charge. So this is going to give us a total of 18 electrons. We'll put the nitrogen in the middle and oxygen's on the outside because it's listed first and it's closer to the middle of the periodic table. We'll fill our octets. And when we do our electron count, we have 12 in lone pairs around the 2 oxygens, and another 4 around the nitrogen, so that's 16, and then the 2 bonds make 18 and 20 electrons too many. So take away a pair from the nitrogen and an oxygen, make another bond, and that gets our electron count right. Square brackets and charge would be appropriate here, but we're interested in the shape. So we'll look at the steric number as being a 3 because there's 1 lone pair, 1 double bond, 1 single bond. Each of those counts as 1. So our steric number is 3. That means the electron geometry is going to be trigonal planar. But because we have 1 lone pair, that means our molecular shape is actually a bent 120. CH4. Carbon gives 4 electrons. Hydrogen gives 1 electron each, so that's 4 electrons total. So this should have 8 electrons in the structure. We put our central carbon with the 4 hydrogens around it. Carbon already has a full octet. The electron count is 8, so that's perfect. Lewis structure is done. Steric number is 4, so the electron geometry is going to be tetrahedral. There are no lone pairs, so that means the molecular shape is also going to be tetrahedral. NH3, nitrogen, 5 electrons. Hydrogen, 3 electrons because there's 3 of them and they're 1 each. No charge. 8 electrons on the structure. Central nitrogen. Hydrogens around it. Nitrogen needs a lone pair for an octet. And there's our Lewis structure. Steric number is going to be 4 because we have 3 bonds and 1 lone pair. So the electron geometry is going to be tetrahedral. We have 1 lone pair with that steric number 4. That means the molecular shape will be trigonal pyramidal. Water, H2O. We've done water a bunch of times. I don't think we have to go through all the steps. That's the Lewis structure for water. The steric number is 4. 2 bonds, 2 lone pairs. And because there's 2 lone pairs and a steric number of 4, that means that this is a bent 105 molecular shape. PCl5. Phosphorus, column 5, That's going to give us 5 electrons. Chlorine is column 7. 5 of them will give us a total of 35 electrons. So when we add this up, we should have 40 electrons in our structure. Let's put phosphorus in the center. Put our chlorines around the outside. And then fill octets. Each chlorine gets 6 electrons in 3 lone pairs. And since there are 5 of them, 5 times 6 is 30. Phosphorus already has a full octet. Let's count the electrons in the bonds: 32, 34, 36, 38, 40. The structure is good. Steric number is 5, because there are 5 bonds. There are no lone pairs, so that means the molecular shape is trigonal bipyramidal, just like the electron geometry would be. SF4. Sulfur, column 6, 6 electrons. Fluorine, column 7, 4 times gives a total of 28. So this structure should have 34 electrons in it when we're done. Put the sulfur in the center, 4 fluorines around the outside. Sulfur has a full octet, but the fluorines don't. So we'll stick in our electron pairs to fill that octet for each fluorine. That's going to be in lone pairs around the fluorines, a total of 6 times 4, which is 24. And then with the bonds, we have 26, 28, 30, 32. That's not enough electrons. So on the central sulfur, we're going to put another pair. This gives us a steric number of 5, 4 bonds and 1 lone pair. So the electron geometry is going to be trigonal bipyramidal. But since one of our electron pairs is a lone pair, that's going to result in a seesaw shape. ClF3. These are all halogens, and there's 4 of them total. So that's going to give us 28 electrons in our structure. If we put chlorine in the middle, fluorines around the outside, fill octets, we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, and then 22, 24, 26. With the bonds, we need another pair. So now we have steric number 5. So the electron geometry is trigonal bipyramidal. But with 2 lone pairs in the equator, that leaves us with a T-shaped molecular shape. I3. Again, it's 3 halogens, so that's 21 electrons, plus another one for the charge. So that's 22 electrons in the structure. Put I, and then another I, and then another I, and fill octets. 2, 4, 6, 8, 10, 12, 14, 16, and with the bonds we have 18, and then 20, so we need another lone pair around that central iodine. Steric number is 5 again, so the electron geometry is trigonal bipyramidal. But since we have 3 lone pairs in the equator, this ends up just being a linear molecule. SF6, sulfur, 6 electrons. Halogens are 7, and there's 6 of them, so that's 42. 6 and 42 makes 48 electrons. Put the sulfur in the middle. And 1, 2, 3, 4, 5, 6 fluorines around it, and then fill octets. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, and then counting the bonds, 38, 40, 42, 44, 46, 48. So this is our structure. Steric number 6. So the electron geometry is octahedral, and because there are no lone pairs, the molecule is also an octahedral shape. Next, BRF5. Bromine and fluorine are both halogens, so that's 6 halogens in total, 7 electrons each, so that should give us 42 electrons in our structure. Put bromine here, put my fluorines around it. Bromine already has a full octet, so I'm going to fill fluorine octets. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. And then counting the bonds, 32, 34, 36, 38, 40, not enough. Need another lone pair on the bromine. Steric number is 6 because we have 5 bonds in one lone pair. Because we have a lone pair, the electron geometry is going to be octahedral, but the molecular shape will be square pyramidal. Here's another one, xenon tetrafluoride. Xenon is column 8, so that gives us 8 electrons. Fluorine is a halogen. 4 times 7 is 28. So that means our structure should have 36 electrons when it's done. We'll put xenon in the middle. Fluorine's on the outside. Halogens usually go on the outside. And fill octets. Xenon's good, but fluorines each need 3 more pairs. So that's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. And then with the bonds, it's 26, 28, 30, 32. We need 2 more pairs. Put them on the central atom to make our 36 electrons. The steric number is now 6 because we have 4 bonds and 2 lone pairs. So that means the electron geometry is octahedral. But because we have 2 lone pairs, we end up with a square planar for a molecular shape.